All right. So more on deadlock avoidance. Requires that the system has additional operator information available. Is this usually practical?
That doesn't seem to be practical.
No,
Latin's
why
never
not?
practical.
Hmm?
Latin's never practical.
Latin is, oh,
Well,
nice. No, I
when
disagree.
you're saying there's some additional, you need to know ahead of time.
Right, before the
Right.
process begins.
So look ahead. So, I mean, that may be only good in some scheduling, but it's not.
So
it's
some of
a
these,
process.
so some of these things can be determined by the compiler, right? If you're using a certain number of locks, the compiler can figure that out. What locks are you using, what resources, and it could put that into the binary and then have the operating system somehow schedule it. But can you guarantee that every process will have that information?
No.
No. So if you wanted to guarantee that, then you'd have to, if the process doesn't have that information, you would have to scan it first and then load it in, which is never a good idea for an operating system to be doing, because now you're scanning and doing code analysis when you're trying to load the program. Anyways,
Unless you limit it, unless your operating system was very specific and your programmers and such programs you were writing it were specifically, they were meant to do that. I mean, they can't.
true, but is that a robust solution?
No,
Or
it's not. It's
No.
only very specific.
It's very specific. Right, and we don't want to do that to our programmers. But there are a couple things to at least look at here. So simplest, most useful requires each process declare ahead of time, which is great. And then it can dynamically look at the resource allocation and make sure there's no circular weight condition. Sure. State is defined. Let's see. Resource allocation state is defined by the number available and allocated resource and the maximum demands of the process. Right. So the idea is that the OS can keep track of who's getting what and come up with its own internal ordering of things. Wow. Okay, safe state. When a process requests available, sure, safe state is there exists a sequence. Well, we got all the different processes of all of them, and a system such that each PFI, the resource PFI, can still request and satisfy the sure, that's great. AKA safe state. Namely, once it requests a resource, is it going to cause deadlock is all I'm trying to say. AKA, is it going to create a circular weight or a circular pattern? So it needs to keep track of everything that's being resourced, or all the processes resourced, and find out if it's going to create that cycle. And if it would create a cycle, it just denies it. So if it's in the safe state, no deadlocks. If it's unsafe, there is a possibility of deadlock, although not guaranteed, because you may have a cycle that is executing, but maybe an extra process on the side that could free its resource eventually and then break the cycle.
Is there a Sith Lord in the back?
I was trying to figure out who made that sound. Thank you, Chris.
It wasn't intentional.
Was or was not?
It was not intentional.
Okay. All right, so avoidance is just make sure it never reaches an unsafe state.
It's very scientific.
Very scientific. All it's saying is that if you're in the safe state, you can't have deadlock. If you're in an unsafe state, you might have deadlock. All right. Okay, so avoidance algorithms. Again, these are not implemented in kernel. Single instance, you have the resource allocation, and the last one, of course, is the banker's problem, or algorithm, I should say. Okay, please tell me you give me a picture of this. Thank you. Claim edge. So process, claim, process may request the resource represented by the dashed line. AKA over here, P1 and P2 may request R2. Claim edge converts to a request edge when a process requests the resource and therefore is given the resource, so that's going to hold it. request is converted to an assignment edge when the resource is allocated to the process. Okay, so I was saying that these two steps happen at the same time. In general, they're going to pretty closely. When a resource is released by a process, it goes back to a claim. And the resources must be claimed a priori to the system. In other words, all these arrows exist to the beginning, in the very beginning before the processes start. Again, that would require a priori knowledge of some sort. You have to do either code analysis or have the compiler put that into your binary when it loads. So over here we're saying that P1 holds R1 and P2 is currently requesting R1. And they both may claim R2 at this point if they wish. And then if if P2 gets a hold of R2, it would look like this. But
Then you have deadlock.
we are in an unsafe state. We don't necessarily have deadlock because P1 may claim R2, but it has not requested R2 yet.
Right, okay, I'm assuming single instances.
Yeah,
That's
the
right.
dotted line just means that it may request it. It has not requested it yet.
Okay, gotcha.
See, so right here, P2 may request R2, but it hasn't yet.
Right.
Now it has. So P1 may request R2, but it hasn't yet. So
Right.
there's no deadlock yet, although we're unsafe because we have a cycle.
But we know P1 is eventually gonna want R2.
We don't know. Well, it may or may not. It may release R1 before it wants R2. And P2 is just a hog right now. Actually, no, wait, there wouldn't be deadlock. Because even if it tried to grab R2 and there was nothing available for it, P2 is requesting R1. Never mind. I see it. I thought the arrows were going the other way. So yeah, this could still be deadlock. All right, so process P sub I request RJ. The request can be granted only if converting the requesting edge to assignment edge does not result in the formation of a resource of a cycle in the resource allocation graph. Basically, we're good. Can't be done because now we have a cycle. Notice that the cycle is based on the direction of the arrow. Everyone okay with that? Right, so P2 would not be granted the R2 resource. But P1 could be eventually given R2 and hopefully would eventually give up the R1 resource. Oops.
How would P2 request, from this point,
Mhm.
how would it request R2 if it's waiting on R1?
So it's requested R1.
But it hasn't gotten it, and then it requests R2?
You can request more than one resource at a time. Yes.
Okay, so, but you're saying, well, 'cause we're using.
When you're coding, of course, I'm sorry, let me answer him real quick. If good programming practice, you would not request more than one resource simultaneously. I understand what you're saying. But this is just an example to get the point across.
But what I was thinking was that the resource, okay. Well, you're saying, okay, we're using the resource allocation graph, and if we were looking at this and saying, okay, hey, we would like to give the resource to P1 instead of P2. We wouldn't give it.
No, what we're saying is currently P1 is holding on R1.
Right.
P2 has asked for R1 and is waiting for it. And we're saying now, what happens if P2 also requests R2?
Then we would have potential for, it would be an unsafe condition.
Right, that would be an unsafe state because there's a cycle. So we would deny that because it would change this, which does not have a cycle, because you can't notice that the arrow is going this way. So you can either go here from P2 or you can go from P2 all the way around, but you can't go back to P2 because there's just arrows.
But you're saying these are not used because it's inefficient, right?
They're inefficient,
Yeah,
right.
Because we wouldn't.
Well, you'd have to be holding this graph in memory the whole time,
Exactly.
first off. And
That's-
then you'd be
yeah.
doing a linear calculation every time someone asked for a resource.
Yeah, you have to do this for every. it'd be-
Right, and how many processors, yeah, it's not a good idea. And, okay, any other questions? All right. Banker's problem, or algorithm, keep calling it the problem. So now we're going to have multiple instances. Each process must a priori claim its maximum use. When a process requests a resource, it may have to wait. And when a process gets all its resources, it must return them in a finite amount of time. Okay, do we get a picture? Oh, we're just going to like math it? Okay, good. We're going to math it all out. Sounds great. Available, vector, okay. Basically, this is saying how many of each resource is available. It's an array of how many of each resource is available. How many? Matrix, so n by m. Notice that n is the number of processes, m is the number of resource types, and this is the process may request at most k instances of the resource type. This is what would be pulled in from or loaded in from the process when the operating system loaded the process into memory. Allocation, how many of those resources have been allocated to each process. And then need, let's see, P sub I may need k more instances to complete its task. Thank you. Safety algorithm? Let work and finish be vectors of length n and m. So work is initially to available. So work, aka what can be done, or what's available, starts off as what's available. And finish is nothing's finished because we haven't started. So find an I such that both the finish is false and the need is less than the work. Okay, that should be just the beginning. So eventually you'll have that. If no such I exists, then you go to 4. But we'll go on because obviously we're going to find something in the beginning. So the work at that point is work plus the allocation, aka originally available. So we're going to, I always should be, finish should be true, go step 2. So work plus allocation, shouldn't that be subtracting how much? Oh no, that's how much work has been done. Okay.
Work is available.
And available is k instances of resources, so I don't know why it's at. Shouldn't work be keeping track of what's available at the time? Or it's keeping track of what's being worked. Oh no, allocation. There we go. So allocation, right, so work is now work plus whatever is being allocated to it. Finish is true, go step 2. Okay.
Why, if work starts off as being work available, it does seem like it should be subtracted, but why, how is this working again? Or go?
So first off, notice at the end, if finish sub I is true for all I, then the system's in a safe state. So what is this algorithm actually telling you? Is there step 5? No, step 5. Yeah, that's the whole algorithm. It's basically telling you if the system's going to be in a safe state or not. All right, lots of blank look.
Yeah, because I'm still getting confused about the work equals available, because that's
So what's available?
right.
It is vector of length m. If available, there are k instances of resource type available. So in the beginning, there's so many instances of each resource. Maybe
So
one
work is
resource.
actually the vector of like it.
Right.
And then you're going to go through and step 3, work is equal to work plus the allocation.
Right. And then the allocation, where we got
Is
So you're adding to the work everything that's been allocated to the process.
But if you do that, then when your availability drop.
Yes. Because,
Oh, never mind. That's an idiot. I'm not an idiot, but it's just like, that don't make sense. Okay, it doesn't matter. We don't care about available once we go through this.
and we're basically saying if finished sub I, aka every process can be allocated something without causing a cycle, then we're saying we're in a safe state. All right. Oh my goodness. Resource request.
Wait a minute.
Basically, the algorithm is checking
In
to make
step
sure.
2, if you have a need that's greater than work,
Right, need, see, need sub I, then P may need more instances to complete its task. So, need sub I, so each is K. The need is the max, knows that process may request the most K instances of resource 1, so the allocation is how many things have been allocated to it. So, of course, the need is how many it needs left, how many it needs to complete.
so if the need is less than the work though,
Because work is supposed to be keeping track
or
of it.
greater than work, so if you need
This,
more than what's available.
Whoa, hold on. This should be a subtraction, shouldn't it? Yeah, that's supposed to be subtraction. Right? Because the work you're subtracting.
I keep thinking that, but
Yeah, these
But-
slides.
I keep thinking that, but once we see the work is equal to available to begin with, then we don't care what availability is.
Well, no, it starts with what's available, and then you're
Right.
subtracting what's been allocated. All it's saying is you grab the process, grab a process where you can actually satisfy what it needs, satisfy what it needs, subtract that from what's available, because we're keeping track of that as work, that should really be
Right.
subtraction. Mark it as done, go see if you can find another one.
And then you basically see, okay, now our availability has gone down, which is less than work. So at the next one you're checking, you're going like, wait a minute, there's not
So
enough
if you have
resources
two
available.
processes,
Yeah,
one
that-
that needs something that the other one's working on,
That
you're
makes
gonna mark the
sense.
first one as done, but never reallocate it or release the resources.
Correct.
You're trying to do multiple processes.
What is this algorithm actually telling you?
You said if it's in a safe state or not.
Right.
No.
If
It's
all the
keeping us in a
processes
safe
that we're
state.
waiting on, if there are resources available for all of them.
Yes. Namely, we're in a safe state. But yes. That's all this is doing.
Yeah, that was
Sure. Yeah, it's because you had so many arrays and matrices. Resource request out request equals what? Request vector for P, then process K, then if request sub J equals K, then process P wants K instances of resource J. Right. So the first check is make sure that it's actually requesting something within its need, because if it's not, then that means that your a priori analysis was incorrect. If request is less than available, go to step 3. Namely, if those available, if it's actually available, continue on, otherwise, must wait. Sure. Ooh, we get to pretend to allocate the resources by modifying the state as such. All right. And if safe, the resources are allocated, unsafe, continue on. In other words, you pretend, you come up, you make a copy of that graph, you make this change, then you run the safety algorithm to figure out if it's in a safe condition, and if it is, then go ahead and allocate it. If not, then it must wait.
This is used?
No, I said that from the very beginning. None of this is used.
Yeah, I was like, where's that?
No. In the very beginning, maybe I should put that big bold
No, I
line.
said something like this.
Nothing you see today is used.
Right. most operating systems just pretend like deadlock doesn't occur.
But in an ideal world, we have enough speed, enough processing.
Well, even then, we want
Why
to.
would we do it? Yeah.
Why we wouldn't want to do that because we don't want to sacrifice that much performance. All right, here's an example. 5 processes P 0 through 4, 3 resource type. A has 10, B has 5, and C has 7. Okay, great. Snapshot at time T0. Oh, okay. Allocation, this for, remember, this is for A, B, C. For each of the processes, that's what they've been allocated. This is how many they're allowed to have at most. And this is what's available from A, B, C. All right. Content of the matrix need is defined by max minus allocation. So back here, you take max, everything in here, subtract allocation, you would get this thing over here. System is in a safe state since the sequence satisfies the safety criteria. Let's see, P1, P3, P4, P2, and then P0. Did they ever define you what the safety criteria was? I guess not. Really? Huh. Well, it's safe because there's right now we're saying there's no cycle. But we don't have the picture of the graph out there for you. Great. Okay. So now we're saying let's pretend that P1 requests 102. All right. Check that the request is less than available. That is 102 less than 332? Yes. So those resources are available. That's the first one. And actually, you're first supposed to check if their P1s, was it the request plus allocation is less than need, or max, I should say, to make sure it didn't go over its maximum request allotment. But we're just assuming that for the time being. Yes, John? Oh, yeah,
What request are we looking at right now?
P1
Oh,
requests 102.
All right. And P1's got 302 to begin with.
Yes. And we're going to add 102. And this graph is slightly off, of
And
course.
the availability is 2, so yes, 230.
Let's see if I can fix that real quick. Perfect.
Okay, so now we're checking the availability. What we've got available is 230.
Right. So what we're going to do is notice that, well, we didn't have 302, did we? We had, no.
Because those numbers don't look, because you'd be checking against what's available. Unless that's, since 302 is already after it's requested, that's what it's getting.
All right. So that is, all right. So check the request. That is unless that's true. Oh, why these numbers don't look right?
What was P1 to begin with before that?
I would assume it's 1,
1,
2, 2, but now it's going to 302.
Yeah, it shouldn't do that because if you're doing, it should be 2.
Wow, what's up with these slides?
Math.
Math is hard. Oh, no, this is need. I'm sorry. This is need. Now I see what we're doing wrong. That's need, and this is the allocation. Now that makes sense. So beforehand we're looking at the need, and you notice that the need went from 122, how much it needed, to 021, which makes sense because it was a proper subtraction.
Gotcha.
And then available went from 332 to 230. Okay,
Gotcha.
good. So now we're up.
Wish it was all on the same.
Yeah. Safety algorithm shows that the sequence P1, P3, P4, P0, P2 satisfies the requirement, so that we're still okay, it's safe. Now the question is, can the request for 330 by P4 be granted? Now it should be easy.
No.
Why?
The first resource, so you got 2 and they want 3.
Right.
They're requesting, hey, and
It's not available. It's not available. So that can't be granted. How about 020 from P0?
Yes.
Okay, hold on. So that's available. And then, but if you grant it, is that going to satisfy the safety problem?
Oh. It should, because you're not messing with what's available. I mean, it should, because you've not messed with anything else. You've only taken what's available.
Right. You've already, and P0's already been allocated this resource, so it's getting more, and then allocation. I have one, but what's the need? It's not apparent from this picture. You'd have to draw it out to answer that question. All right. You'd have to draw it out to answer this question. All right, deadlock detection. All right, so that was avoidance. Not used. Deadlock detection, also not used. Allow the system to enter deadlock state. Okay, now that part we do allow. We do that. We detect it. We don't do that. And then we try and recover somehow. Oh boy. Which of these three is the hardest one if we were going to implement it?
Recover.
Yeah. Why?
Because you have to determine what it had done and see if you could undo it, which may not even be possible.
Correct. Basically, I have to have a time machine for your entire process. Not pragmatic. All right. All right, so we have a wait for graph. Nodes are processes waiting for P. Periodically invoke an algorithm, search for a cycle in the graph, and if it does, it's deadlock. All right, that should be intuitive. An algorithm to detect a cycle in the graph requires order of n squared operations, where n is number of vertices in the graph. Ooh, that's slow. All right. So let's see. Here's the resource allocation graph. You can convert it to a weight graph because basically what you're doing is compressing the resources into one long arrow. Because what you're saying is P1 wants to get R1, but R1's held by P2, therefore P1 is waiting on P2. That's all we're saying here. So whenever you have a resource in between, you're basically converting that into a wait for graph over on the right. You good? Matt is all about this. Hey, look at this stuff again. Available, linked in indicates number of available resources, allocation, number of resources allocated to each process, and then request, what is it, the current request of each process. All right, how do we detect it? Work starts with anything available. So, everything. For I1 to n, if allocation does not equal 0, then finish is false, otherwise finish is true. All right. For each index in I such that finish is by default, if there exists no such I exists, go to step 4. Wait, what? Hold on. Oh, we initialize it. Okay. Works available, and then for, okay, if allocation does not equal 0, then finish is false, otherwise finish is true. Because if it has 0, then obviously it's done. It doesn't need anything, or it hasn't got anything allocated. Find an index I such that both is false and the request, aka it can actually do some work. Go ahead and mark that work, and there it is again with the plus. Must mean something different. Maybe allocations and negatives. You just keep doing that. This should look very similar. And then at the end, if finish is false for any I, then the system's in deadlock. Moreover, finish the by is false and P, then that process is actually deadlocked. This is an m by n squared algorithm to detect whether system's in deadlock, aka very slow. You okay, Matt? Yeah. So is this, let's see. Is this in a deadlock? That's the question. Answer is no. let's see, because he's requesting 2 and 2, which are being held by this guy. Let's see, him, P2, P4, but not P0, and he's requesting P1, or just 1, which is being held by other of these guys, which are not. So there's no cycle, or there's no full cycle. Okay, P2 requests an additional resource of type C, so the request, so now we have one over here. State of system can claim resource held by process C, but insufficient resources to fill out a process request, so the deadlock exists. All right, let's go back and look at this. So what they're saying is if we put P2, put a 1 right here, now we're going to have some deadlock. Although that's interesting because then P0 is not waiting on anything. Well, because so you put a 1 right here.
You only have 5 of that, 6 of that resource total.
Correct. And so what's going on is P2 is holding on to 3 of them. He wants another 1. So he's waiting to release his 3. P2 is also waiting on the same thing to release his 2. P3 also has it, but he's waiting on P1 or A to be released, which can't be released by P0 because the other people are actually holding on to it, so then deadlock occurs. Was that a yes or a no, Matt?
That'd be easier to see if you drew it out. Yeah, I know, like you said, grab it.
All right. Let's do the weight graph. All right, those at home, I'm about ready to draw this on the board by just doing the processes. So we have P sub 0. And who is P sub 0 waiting on? No one. All right, then we got P sub 1. Who's P sub 1 waiting on? Now hold on, let's draw all of them out. Actually, let's draw them in a circle, otherwise this is going to get ugly really fast. All right, what's P sub 1 waiting on? Anything that has A or C, which is P3, wait, I'm sorry, A or C, which is P3, right?
Yes.
And anyone else?
P2?
P2. And P4?
Oh, P4 doesn't have anything. Oh, wait, A or C, you said.
Yeah, so he, no cycles yet, we're good. And then go give the people at home a picture. Ooh, nice good glare right there. All right. P2, is he waiting on anyone? No. P3, is he waiting on anyone? He's technically waiting on P1. That's a cycle. So hang on. To get to that. And he's waiting on
P2.
And he's waiting on P1 and P2. Right. Okay. So it looks like there's a cycle right here, but it's actually not necessarily deadlocked.
Are we drawing our arrows in the correct direction? If we're waiting,
P1's waiting on P3.
so would the arrow go the other direction?
All right, let's double check. I wouldn't. So if P1 requests the resource 1, but resource 1 is being held by P2,
Oh, never mind.
then we're saying that
Yeah,
P1
okay.
is waiting on P2.
Okay, gotcha. So we're looking at P3, what it's waiting on.
P3, we're done, and then P4 is waiting on P. Really, is waiting on P2. All right. So the one thing that looks like a cycle is between P1 and P3. And the reason that that is not actually a cycle,
This P2 does not,
because the reason that's not technically a cycle is P2 could release it and get rid of this actual weight. So this is kind of a fake pointer. That's what's going on. All right. So the next question is, what happens when P2 requests another instance of resource 1? Well, if P1 is requesting the instance, oh, people at home, there's the picture. Go ahead and pause it. All right, so if P2 is going to request 1 right here, he is now going to wait on P3 and P4. So P2 will wait on P3 and P4. P2 will wait on P3 and P4. And now we actually have a true cycle. Oh yeah, there's a cycle right there. You can also have a cycle. And you also have another cycle right here, another cycle over here. Those are actually true ones. Okay. Did that answer your question, any? If I wanted to be really verbose, I would put all the resources in there for this graph. That graph will get ugly really fast. But this is the idea. The only reason that this one wasn't a true cycle is the way the resources were shared between the two. Oops. Okay. Here's another good question. How often is deadlock? Okay, when and how often should we invoke this algorithm?
Never,
Why?
because it's horrible.
It's a horrible algorithm. Right. So we should never do it, but that's a big problem if we wanted to, is when do we actually try to detect it?
As little as possible.
As little as possible. What you may be able to do in the operating system, if you realize all the processes that are using a lock are all waiting on something, maybe run the algorithm then. If they're all waiting on I/O, don't do anything. That's just I/O. So there might be a couple of things you can do to run this algorithm, but in general, it's not a good idea.
well, also you run into things, one of your indicators would be your availability.
Right.
Because if your availability was like 8-0, you're like, well, somebody's getting, need something.
Yeah. Right. Okay, yeah, that's true too. But you don't know, the problem with that is a process may be finishing up to release it, right? Yeah. Okay, recover, abort all the deadlock processes, abort one process at a time until everything's eliminated. So abort all the deadlock processes. I like that one, that's simple. Y'all were bad. Abort one process until the deadlock cycle is eliminated, so maybe something can run. Okay. And which order should we abort? Oh boy. Priority. Which one's long? You have different ways to select it, to decide who should be aborted. Again, not implemented. Selecting event victim, you want to minimize the cost, so maybe the simplest process should be killed first. Yeah, so starvation. If you keep killing the same victim, maybe that's a bad idea. Try and, wow, that came out weird.
No, I was just saying to some opera, somebody took it off the operator. So I'm pretty good user. Where are all my
Maybe once
processes?
maybe process inversion if it's been killed off a lot as well. Okay, good. End of chapter 7. All right. So what do we learn from chapter 7?
Don't do this.
So deadlock, it happens, and we do nothing about it. But hopefully from chapter 7 you'll learn why the operating system does not deal with deadlock for you, and it's the programmer's problem.
Basically smart programming.
Right. Well, why is the operating system not doing this for you? It's the biggest thing. So when you do your homework, you're going to be going through these problems of running the banker's algorithm, and just remind yourself this is why the operating system is not doing it. No, you're supposed to say, yeah, because that means this is the last time you have to deal with it, right?
I just want to be like m squared. You know.
Oh, what's the answer? Oh, sub m squared. That's a good one. Any questions about chapter 7? All right, so your homework has been put up for chapters 6 and 7.
What chapter are we on?
7. So 6 and 7 from last time. So go ahead and get started on that. And look, you have an hour. Yes?
Make it help my life.
Yes, you can, and I will.